Welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 113, titled PathSum 2. This is a popular problem that tests your understanding of tree traversal and pathfinding techniques. Let's dive in and explore how we can approach this efficiently. In this problem, we're working with a binary tree. Your task is to find all root-to-leaf paths where the sum of the node values in each path equals a given target sum, which is provided as an integer. A root-to-leaf path starts from the root node and ends at any leaf node. Remember, a leaf node is defined as a node that doesn't have any children. The input consists of two components, the root of the binary tree, represented as a tree node, and the target sum, an integer. The output is a list of lists, where each inner list represents the node values along a root-to-leaf path that satisfies the condition. For example, if the tree and target sum are given as described here, we'll see how this works in an example shortly. Here's the first example. The input binary tree is represented in array form as 5, 4, 8, 11, null, 13, 4, 7, 2, null, null, 5, 1, with a target sum of 22. The tree can be visualized as shown, with the root node at 5, branching into two subtrees. One of the valid paths is 5 to 4 to 11 to 2, which sums to 22. Another valid path is 5 to 8 to 4 to 5, which also sums to 22. Therefore, the output is a list containing these two paths, 5, 4, 11, 2, 5, 8, 4, 5. This demonstrates how we identify all root-to-leaf paths that meet the target sum condition. Now let's look at a second example. Here, the binary tree is much simpler, with nodes 1, 2, and 3. The target sum is 5. Visualizing the tree, we see the root node 1 has two children, 2 and 3. However, neither of the paths 1-2 or 1-3 adds up to 5. As a result, there are no valid root-to-leaf paths that meet the condition, and the output is an empty list. This highlights that not all trees will contain valid paths. In the third example, the input tree is even smaller, with only two nodes, one is the root and 2 as its left child. The target sum is 0. When visualized, the tree shows a single path from the root to its only child. The sum of this path, 1 plus 2, equals 3, which does not satisfy the target sum of 0. Thus, the output again is an empty list. This example helps illustrate that the function should handle cases where no valid paths exist, even in very small trees. Finally, let's discuss some important constraints and edge cases. The number of nodes in the binary tree can range from 0 to 5,000, and node values can be as small as -1,000 or as large as 1,000. The target sum can also be a large positive or negative integer, up to 10 to the power of 9 in magnitude. For edge cases, if the tree is empty, meaning the root is null, the result should be an empty list. In a single node tree, check if the node's value matches the target sum. Negative node values are allowed, so paths with negative contributions should be considered valid. If no paths satisfy the condition, the result must be an empty list. Lastly, if there are multiple valid paths, all of them must be included in the output, even if they result in the same sum. These considerations ensure the solution is robust and handles all scenarios correctly. To tackle the PathSum 2 problem, one straightforward approach is to use a recursive depth-first search to explore all possible root-to-leaf paths. The idea is to traverse the tree, keeping track of the current path and the cumulative sum of the node values. When we reach a leaf node, we check if this cumulative sum matches the target sum. If it does, we record the path as a valid solution. This method is intuitive and simple to implement, but it comes with trade-offs. Specifically, copying the current path at each leaf node can be costly in terms of time, especially for larger trees. In the worst case of a balanced tree, the complexity can reach n squared, where copying the path contributes to the overhead. Additionally, it requires extra memory for the recursive stack and the storage of intermediate paths, which may not be optimal for certain scenarios. While this approach is easy to understand, its memory inefficiency makes it less practical for larger or deeper trees. A more efficient strategy builds on the brute force approach by introducing backtracking to reduce memory usage. Instead of making a copy of the path at every step, we modify the path in place during the recursion and revert those changes upon backtracking. This approach still uses depth-first search but optimizes memory by avoiding unnecessary list duplications. At each leaf node, if the cumulative sum matches the target, we make a copy of the current path and save it as a valid solution. This method retains the same time complexity of O(n) squared due to path copying at leaf nodes, but it is more memory efficient during traversal since we use a single list for the current path. While it requires careful handling of the path list to ensure correctness during backtracking, this optimized approach strikes a better balance between performance and memory usage compared to the brute force solution. Another alternative is to use an iterative depth-first search with an explicit stack. This replaces recursion with an iterative process, which avoids the overhead of a recursive stack and can be particularly useful for very deep trees. The idea is to maintain a stack where each entry contains the current node, the cumulative path, and the cumulative sum. As we process nodes, we pop them from the stack, evaluate their cumulative sums, and push their children back onto the stack for further exploration. When a leaf node is encountered, we check if the cumulative sum matches the target and, if so, record the path. This approach shares the same time complexity as the recursive methods, O(n) squared, since we still need to copy valid paths at the leaf nodes. However, it avoids risks like stack overflow in the case of extremely deep trees. While effective, the iterative DFS can be slightly more complex to implement and might not offer significant advantages for most practical cases. Ultimately, the optimized backtracking approach is the most suitable strategy for solving this problem. It offers a good balance between clarity, efficiency, and scalability. By modifying the path list in place and reverting changes after exploring each branch, we minimize memory usage while maintaining simplicity in the recursive structure. Though we still need to copy valid paths at leaf nodes, which contributes to the O(n) squared time complexity, this is an unavoidable aspect of the problem and does not outweigh the advantages of this approach. Compared to the iterative DFS, backtracking is easier to understand and implement, making it more accessible for general use. While careful path management is necessary, this trade-off is manageable. For most practical inputs, this solution is both performant and straightforward, making it the ideal choice for solving path sum 2 effectively. To solve the problem of finding all root-to-leaf paths in a binary tree where the sum of the node values equals the given target sum, we can break the algorithm into 3 primary steps. First, we define a recursive function to traverse the tree. The base case is straightforward: if the current node is null, there's no path to process, so we return immediately. Next, we handle the case where the node is a leaf, meaning both its left and right children are null. If this is true, we calculate the path sum by adding the current node's value to the running sum. If this total matches the target sum, we add the current path to our result list. After handling the base case and leaf nodes, we proceed to the second step, which is performing a recursive depth-first search on the left and right subtrees. For each recursive call, we include the current node's value in the path and pass the updated path and running sum to the child nodes. Finally, once we've explored both subtrees, we implement backtracking. By removing the current node from the path, we ensure the path is appropriately reset and ready for exploring other branches of the tree. Depth-first search, or DFS, is particularly well suited for this problem because it allows us to systematically explore all root-to-leaf paths while keeping track of the current path and sum. One of the key techniques here is backtracking. Backtracking ensures that after exploring a node's subtrees, we remove the current node from the path, effectively resetting the path for the next branch of the tree. This prevents unnecessary duplication and ensures correctness. From an efficiency standpoint, the algorithm traverses each node exactly once, making the time complexity O(n), where n is the total number of nodes in the tree. The space complexity is dictated by the recursive call stack, which can go as deep as the height of the tree. In the worst case of a skewed tree, this height could equal the total number of nodes. Additionally, we use a path list to track the current path being explored and a result list to store all valid paths that meet the target sum. These data structures ensure the algorithm is both organized and efficient. It's also important to keep edge cases in mind, such as trees with only one node or those containing negative values, to ensure the solution is robust in all scenarios. When addressing edge cases, the algorithm must handle situations like an empty tree, where the root is null. In this case, we simply return an empty list, as there are no paths to consider. For a single node tree, we check if the value of the node equals the target sum, as the only path would be the node itself. Additionally, the algorithm should handle trees with negative values, ensuring that the sum calculation and comparison still work correctly. The pseudocode implementation of this algorithm provides a clear structure. The main function, findPaths, initializes a helper function called DFS to perform the depth-first search. This helper function takes the current node, the path being tracked, and the running sum as inputs. Within the function, we first check if the current node is null and return if true. Otherwise, we add the node's value to the path and update the running sum. If the node is a leaf and the running sum matches the target sum, we append a copy of the current path to the result list. To explore further, we recursively call the DFS function for the left and right children, passing the updated path and sum. After these recursive calls, we perform backtracking by removing the node from the path, ensuring it does not affect other branches of the tree. The final step of the implementation is invoking the DFS function from the root node, initializing the path as an empty list and the running sum as 0. The result list, which stores all valid paths, is returned at the end. To better understand how this algorithm works in practice, let's walk through an example. Consider a binary tree where the root is 5, and its left and right children are 4 and 8, respectively. The tree continues with subsequent nodes, as shown. The target sum is 22, and the goal is to identify all root-to-leaf paths where the sum of the node values equals this target. Starting at the root, the initial path is 5. From here, we will explore the left and right subtrees, updating the path and running sum at each step. In the left subtree, the path progresses as 5, 4, then 5, 4, 11. At this point, we explore the leaf nodes, reaching 5, 4, 11, 7, where the sum does not equal 22, and 5, 4, 11, 2, which forms a valid path. This path is added to the result list. Returning to the root, we then explore the right subtree. The path becomes 5, 8, then 5, 8, 13, which is not a valid path. Continuing onward, we reach 5, 8, 4, and finally 5, 8, 4, 5, which forms the second valid path. The algorithm ensures that all potential paths are explored while leveraging backtracking to maintain the correctness of the path at each step. In conclusion, this method effectively balances simplicity and efficiency, making it a robust solution for finding root-to-leaf paths with a target sum. By accounting for edge cases and optimizing path storage, the algorithm is well suited for both small and large binary trees. This Python solution for LeetCode problem number 113, PathSum2, uses a depth-first search (DFS) approach to find all root-to-leaf paths in a binary tree where the sum of node values equals the given target sum. The PathSum function first defines a helper function DFS to perform the depth-first traversal. It takes 3 arguments: the current node, the current path of node values, current_path, and the cumulative sum of node values along that path, current_sum. Base case, if the current node is none, the function immediately returns since there is no further path to explore. Recursive processing, for each node, its value is added to both the current_path and current_sum. If the node is a leaf, i.e., it has no left or right children, and the current_sum equals the desired target sum, the path is added to the result list. If the node is not a leaf, the function recursively calls itself for the left and right children. Backtracking, after processing a node, the last value is removed from current_path to ensure the function backtracks correctly and explores other potential paths without interference from the current path. The result list collects all valid paths, and the function finally returns it as the output. Edge cases, the code handles edge cases such as an empty tree, root is none, by returning an empty list. It also accommodates trees with negative values, ensuring that any valid path with a sum equal to target sum is included in the output. This DFS-based approach ensures that all potential root-to-leaf paths are explored efficiently, with a time complexity of O(n), where n is the number of nodes in the tree, as each node is visited once. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. Here, we begin implementing the solution in Java. The pathSum method is the entry point, which takes the root of the binary tree and the target sum as input. We initialize an empty list called result to store all valid paths and then call a helper method DFS to perform a depth-first search. The DFS method is where the main logic resides. It takes several parameters: the current node, the target sum, the current path being explored, the result list, and a running sum that tracks the cumulative value of the current path. Now, in the DFS method, the first step is the base case. If the current node is null, we simply return because there's no work to be done. Next, we add the node's value to the current path and update the running sum. Then, we check if the current node is a leaf, meaning it has no left or right children, and if the running sum matches the target. If both conditions are true, we've found a valid path, so we add a copy of the current path to the result list. From there, we continue the depth-first search by recursively calling DFS on the left child. We also make a recursive call to DFS on the right child to explore all possible paths. Once we're done processing the current node and its children, we backtrack by removing the last node from the current path. Backtracking is essential because we need to restore the state of the current path for further exploration without affecting other branches of the tree. Finally, this code snippet includes the definition of the treenode class, which represents a single node in the binary tree. Each node stores its value, a reference to its left child, and a reference to its right child. This definition makes it easier to construct and traverse the tree during the execution of the algorithm. With this setup, our implementation efficiently finds all paths that sum up to the target value while ensuring that the state of the current path is managed correctly using backtracking. In PathSum 2, the task is to identify all the paths from the root of a binary tree to its leaf nodes where the sum of the node values matches a specific target. For example, in the given tree, we are looking for paths where the sum of the node values equals 22. Starting at the root with value 5, the tree branches out into left and right subtrees. To solve this, we will use a depth-first search (DFS) approach to traverse every possible root-to-leaf path, keeping track of the current path and its cumulative sum. If we reach a leaf node and the sum matches the target, we add that path to our result. Otherwise, we backtrack and continue exploring other branches of the tree. This systematic exploration ensures that we examine all possible paths for valid solutions while avoiding unnecessary computations. To begin, we start the DFS traversal at the root node, which has a value of 5. Here, the current path is just 5, and the cumulative sum is 5. Moving to the left child with a value of 4, we add this to the path, updating it to 5, 4, and the cumulative sum becomes 9. Continuing further down to the left child with a value of 11, the path becomes 5, 4, 11, and the cumulative sum increases to 20. At this point, we explore the left child with a value of 7, resulting in a path of 5, 4, 11, 7, and a sum of 27. Since this is a leaf node and the sum doesn't match the target, we backtrack and explore the right child of 11, which has a value of 2. This gives us the path 5, 4, 11, 2, and a cumulative sum of 22. As this is a leaf node and the sum matches the target, we add the path to our result list. Afterward, we return to the node with value 4, then backtrack further to the root to explore the right subtree. Visiting the right child with a value of 8, the path becomes 5, 8, and the sum is updated to 13. Exploring its left child next, which has a value of 13, results in a path of 5, 8, 13, and a sum of 26. Since this is a leaf and the sum doesn't match, we backtrack to check the right child of 8 with a value of 4. The path becomes 5, 8, 4, and the sum is now 17. Now, from the node with value 4, we explore its right child, which has a value of 1. This gives us the path 5, 8, 4, 1, with a cumulative sum of 18. Since this is a leaf node and the sum does not match the target, we backtrack completely. At this point, the traversal of the initial tree is complete, and the only valid path that meets the target sum of 22 is 5, 4, 11, 2. This demonstrates how the DFS approach systematically checks all potential paths while ensuring no valid paths are missed. In contrast, if we consider a different tree structure where no paths meet the target sum, the process will still traverse all possible paths to confirm the absence of valid solutions. For instance, in a simpler binary tree with root value 1, left child 2, and right child 3, the target sum is 5. Starting the DFS traversal at the root, the initial path is 1, and the sum is 1. Exploring the left child with value 2, the path becomes 1, 2, and the sum is updated to 3. Since this is a leaf node and the sum doesn't match the target, we backtrack. Next, we explore the right child with value 3, resulting in the path 1, 3, and a cumulative sum of 4. This is also a leaf node, and the sum still doesn't match the target. With no other paths left to explore, the traversal concludes, and the result is an empty list, as no paths in this tree meet the target sum of 5. Finally, let's consider a tree where there are multiple valid paths. In this case, the root is 1, with left and right children 2 and 3 respectively, and the left child further branches into 5 and 4. The target sum is 8. Starting at the root, the initial path is 1, and the current sum is 1. Moving to the left child with value 2, the path becomes 1, 2, and the sum is updated to 3. Continuing down to the left child with value 5, the path updates to 1, 2, 5, and the sum matches the target. Since this is a leaf node, we add this path to our result. After backtracking to the node with value 2, we explore its right child with value 4, leading to the path 1, 2, 4, and a sum of 7. As this is a leaf and the sum doesn't match, we backtrack to the root and explore the right child with value 3. This gives the path 1, 3, with a sum of 4. With no further nodes to explore, the traversal ends. The result is 1, 2, 5, showcasing how the algorithm captures all valid paths in cases with multiple solutions. The time complexity of this solution is O(n), where n is the number of nodes in the binary tree. This is primarily due to the depth-first search, or DFS, traversal. In DFS, we visit each node exactly once, performing constant time operations like adding the node's value to the current path or checking if it's a leaf node. This contributes O(n) to the time complexity. Additionally, when a valid path is found, we create a copy of the current path and append it to the result. Copying a path takes O(h), where h is the height of the tree. In a worst-case scenario, such as a skewed tree, the height can be O(n), while for a balanced tree, the height is O log n. Despite this, the DFS traversal dominates the overall time complexity, making it O(n). The space complexity of the solution is influenced by two main factors. First, the recursion stack used during the DFS traversal requires memory proportional to the height of the tree, denoted as h. In the worst case, where the tree is skewed, this height can be O(n), whereas for a balanced tree, it's O log n. Second, the algorithm uses a current_path list to temporarily store the nodes along the path being explored. The length of this list is also proportional to h. Additionally, the result paths are stored in memory, requiring space proportional to the number of valid paths, denoted as p, multiplied by their average length, h. Combining these factors, the space complexity is O(h) plus p asterisk h. In the worst case, this becomes O(n) plus p asterisk n, and for a balanced tree, it simplifies to O log n plus p asterisk log n. When comparing this approach to a naive solution, the advantages become clear. A brute force method might generate all possible paths in the tree and then check their sums, leading to an exponential time complexity of O(2 to the power of n), as there could be up to 2 to the power of n paths in the tree. The given solution, by leveraging DFS and backtracking, avoids generating unnecessary paths and achieves a much more efficient time complexity of O(n). Further optimizations, like early stopping or pruning, are not relevant here unless additional constraints are introduced. For best-case scenarios, such as an empty tree, the time and space complexity reduce to O(1). In average cases, with a balanced tree of n nodes, the time complexity remains O(n), while the space complexity is O log n plus p asterisk log n. For the worst case, involving a skewed tree, both time and space complexities increase to O(n) plus p asterisk n. The mathematical proof of the big O complexity further clarifies the efficiency of this algorithm. The total number of recursive calls equals the number of nodes, n, as each node is visited exactly once, contributing O(n) to the time complexity. Additionally, copying valid paths only occurs when a valid path is found. In the worst case, all leaf nodes could be valid paths. The cost of copying depends on both the number of valid paths, p, and their lengths, h, contributing p asterisk h. Combining these factors results in an overall time complexity of O(n) for traversal and p asterisk h for path copying. This balance between time and space complexity, achieved through DFS and backtracking, ensures the algorithm is both effective and well-suited for solving this problem. When solving tree problems like PathSum 2, there are a few common mistakes to watch out for. First, not handling edge cases, such as an empty tree or a tree with only a single node, can cause runtime errors or incorrect results. It's essential to validate your inputs and account for these scenarios before processing the tree. Another mistake is failing to define the correct termination condition for recursion. Without a proper base case, your program might fall into infinite recursion or yield incorrect results. Make sure you explicitly check for null nodes and leaf nodes to stop the recursion at the right time. Lastly, when modifying shared variables during backtracking, failing to reset their state can lead to errors. For example, if you're constructing path sums, ensure you either use local variables or explicitly undo any changes after each recursive call. This ensures that the state remains consistent as you explore different paths. Another area where errors often occur is confusing the different types of tree traversals: pre-order, in-order, and post-order. Each traversal serves a specific purpose, and using the wrong one can result in incorrect calculations, such as path sums. For path-based problems like this, pre-order traversal is typically the right choice because it processes nodes in the order needed to construct paths. Additionally, inefficiency can arise when the same subproblems are computed repeatedly. For example, recalculating values for overlapping nodes wastes time and resources. To avoid this, you can use techniques like memoization or dynamic programming to store and reuse previously computed results. These optimizations not only save time but also demonstrate a deeper understanding of efficient problem solving. To succeed in interviews involving tree problems, there are a few key insights to keep in mind. Recognizing patterns is crucial. Many tree problems, especially those involving paths, revolve around recursion. For example, root-to-leaf traversal and divide-and-conquer strategies are common patterns you'll encounter. It's also important to be comfortable with tree traversal techniques, pre-order, in-order, and post-order, and understand when each is appropriate for a given problem. Interviewers often assess your awareness of space complexity, especially the recursion stack space. For instance, the space complexity for a balanced binary tree is O log n, while for an unbalanced tree, it can be O n. Furthermore, interviewers may start with a brute force approach and then challenge you to optimize it. Be prepared to suggest improvements like memoization, iterative traversals, or pruning unnecessary branches. Clear communication is also vital. Clearly explain your base case, recursive case, and traversal strategy. Walking through small examples can help illustrate your approach effectively. If you're preparing for PathSum 2, it's helpful to be familiar with related problems that share similar concepts. For example, PathSum, which is LeetCode problem 112, asks whether there's a root-to-leaf path that equals a given sum. PathSum 2, the problem we're discussing, builds on this by requiring you to find all such paths. Another related problem is binary tree maximum pathsum, problem 124, which involves finding the maximum pathsum in the tree, and this path doesn't necessarily have to go from root to leaf. Some root-to-leaf numbers, problem 129, focuses on calculating the sum of all numbers formed by root-to-leaf paths, which is another variation of path-based traversal. Finally, the diameter of binary tree, problem 543, while not directly related to sums, shares similar traversal and recursion techniques, as it involves finding the longest path between any two nodes in the tree. Studying these problems can deepen your understanding of tree traversal and recursion strategies. There are also alternative approaches to solving tree problems that you might consider. For instance, iterative depth-first search, or DFS, can be used instead of recursion. While this approach avoids the risk of stack overflow, it requires managing an explicit stack, which can add complexity. Breadth-first search, or BFS, is another option, where you explore all root-to-leaf paths iteratively using a queue. However, BFS often comes with higher space complexity due to the size of the queue. Dynamic programming can also be applied to store intermediate results and avoid redundant calculations, though this approach might be excessive for simpler tree problems. Lastly, there's Morris traversal, which optimizes space complexity to O(1) by avoiding recursion and explicit stacks. However, it's more complex to implement and isn't always suitable for path-related problems. Each approach has its trade-offs, so it's important to choose the method that best fits the constraints and requirements of the problem. Great job on completing this problem. To summarize, we explored a recursive backtracking solution to find all valid paths in a binary tree. Remember the importance of mastering tree traversal and recognizing when backtracking is a suitable approach. Don't forget to practice similar problems to solidify your understanding. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!